welcome back. In this lecture, we are going to do some examples, and this is a flash distillation problem, and we would understand the importance of activity models. Okay, so what is a flash distillation? Okay, it's typically it segregates the liquid as a solution in liquid and vapor form. Okay. So, this is a problem which we have. The 10 moles per second of the equimolar liquid mixture of water and ethanol at 30 degrees Celsius and 11 kilopascal is flashed to 7.0 kilopascal. So, in other words, we are saying that you have this situation at 7.0 kilopascal, right? So, the question is, what is the resulting composition and molar flow rate of the equilibrium streams exiting the flash distillation unit, which is this one. Okay. So, I mean, it is not in reality it is not simple box, there are many things in between. So, I am not going into details of the equipment structure, but our interest is basically to understand how to solve such a problem, and there is nothing given here, right. So, the first important question is whether the system will flash at all. I mean, that is the most important question, like, how do you know that the system will flash, in a sense will separate? That's something which you have to understand. Okay, is it going to be flashed partially, or will it flash completely to, let us say, vapor phase? So, how do you solve this problem? Let me first explain this. So, these are the questions which would be the first step if you want to solve such a problem. Okay. And in order to address that, you need to pay attention to the basic phase diagram. Let us say this is a PXY diagram. So, we are talking about a generic diagram. So, let us say if I am using a concept from the RAOULT'S law, then I will be able to get something like this. Okay, where the straight line is basically indicative of liquid saturation line. Okay, so this is sometimes also called bubble liquid. This is a bubble point line. So this is a liquid phase, and this is a vapor phase. Okay, this is a bubble point line, and this is a dew point line. Okay. So, bubble and dew. So, first drop of dew is forming, first bubble of vapor is forming. Now, if you pay attention to this, then let us say for a given concentration given in the system, and you asking a question that whether is going to flash partially or fully. So, for a given composition, so in this case it is given equimolar, so it is like 0.51. This would be for a given concentration. You have this. If you draw a line here, what are you going to get? There is two pressures you are going to get, right? So, this will be your bubble point pressure corresponding to equal composition. This will be your dew point pressure. Okay, and if the final structure, final composition for this, if the pressure there is in between that, then essentially you are saying that is going to segregate in liquid and vapor. If it is more than that, if it is somewhere here, then it will flash to liquid phase. Okay, if it is less, it is vapor phase. Now, currently it is in liquid phase. So, basically you are talking about from here whether it is going to flash or not. So, this pressure, whatever the pressure here, if this pressure is above this, okay, the final one, let us say this is 7 kilopascal, right. So, if 7 kilopascal, if the final one is here, then it will not flash at all. If it is somewhere here, then it will flash partially. Then if it is here, then it flash fully to vapor phase, right. So, this is the first step to identify what we are going to do and how we are going to solve this problem, is to first to determine the bubble point pressure and dew point pressure for our mixture at 30 degrees Celsius. Okay. If the bubble point pressure is less than the system pressure, if a bubble point pressure is less than the system pressure somewhere here, we still have an equimolar liquid mixture. Okay. If the bubble point, so somewhere let us assume that So, in order to understand, let us assume that you are here, right, initially, okay, and finally, let us assume that you are keeping the composition fixed. If you are only changing the pressure, if the pressure is system pressure finally is more than the bubble point, then you will have a liquid mixture, but at a different pressure, lower pressure. That is what the statement is. If the bubble point pressure is less than the system pressure, we still have an equimolar liquid mixture, just at a low pressure. Now, if the dew point pressure, which is here, is higher than the system pressure, so this pressure is higher than the system pressure, that means finally the system pressure is below this dew point pressure, which means everything will flash to vapor. So, liquid completely goes to the vapor phase. So, that's a concept here. Okay. So, if the dew point pressure is higher than the system pressure, we have flashed all our mixture to a vapor and now have an equivalent vapor mixture. So, you understand this part, right? So, both scenarios do not result in any separation, which is the point of distillation. So, this is why it becomes important to understand these pressure relations, right? And that is why the phase diagram becomes important. So, what you need is basically your system pressure should be somewhere in between this range in order to separate. Okay. Now, how do you solve such a problem? You do not have anything other than this information, right? But of course, for water, ethanol, you may find a saturation pressure information from Anton equations, which are available widely in the web and as well as many textbook. So, the first important thing is to actually find out this bubble point pressure and dew point pressure. Okay, so let us first look at it. System pressure, the final condition is 7 kilopascal. So, the first thing which we are going to do is basically we will simply consider the Raoult's law to start with. Okay. Now, you know that this, if you add it, you are going to get P, total pressure P, right. Now, how do you get, so remember, 1 is basically water and 2 is ethanol. Okay. So, how you are going to get this one? You are going to make use of Anton equation, right. So using Anton equation. Okay. So, if you use Anton equation from the different test books are available. You can also make use of NIST website, web book, where all this thermodynamics data is available. Then P1 sat at 30 degrees Celsius is 4.25 kilopascal, and P2 sat again at 30 degrees Celsius is 10.56 kilopascal. So, using this, if you add it up, it becomes Py1 plus Py2 is equal to P. This is your x1 P1 sat plus x2 P2 sat. Okay. So, x1 I know, x2 I know. So, and P1 sat I know here, P2 sat I know. So, if you plug in here this information, this is 7.41 kilopascal, which is greater than 7 kilopascal. Okay. So, what it says, this is what we obtain in this case. The first important thing is, what did we obtain here? Is this a bubble point or is a dew point? X here. So, we are talking about X liquid composition. The P corresponds to liquid composition at saturation. So, that will be your, if you look at it here, that is going to be bubble point. Okay. So, this is a bubble point pressure. So, this is a bubble point pressure which is above the system pressure, which is nice, because you wanted bubble point pressure to be higher than the system pressure, but of course, you also want your system pressure to be greater than the dew point pressure. So, let us first again find out what is the dew point pressure. So, since the bubble point pressure is above the system pressure, we know that we do not have all liquid. So, either it is a partially liquid or completely gas, vapor phase. Next, let us determine the dew point pressure to see if we have just a vapor or both liquid and vapor. Once again, we will be going to use Raoult's law to model our system, but now we use it to calculate the dew point pressure. Okay. So, we are going to write again the same way, that we are going to write Py1 x1 P1 sat, Py2 is equal to x2 P2 sat, but then we will get rid of x here. Okay. So, the way we are going to do is Py1 by P1 sat is equal to x1, okay, and Py2 P2 sat is equal to x2, and x1 plus x2 is equal to 1. That means Py1 by P1 sat plus Py2 by P2 sat is equal to 1, or P is common here, this is nothing but y1 by P1 sat plus y2 by P2 sat. Okay. So, this is the expression of dew point, right. So, I can now plug in this expression. So, this is 0.5 by 4.25 kilopascal plus again 0.5 by 10.56 kilopascal, and this comes out to be 6.06 kilopascal, which is less than 7. So, this tells you that since the system pressure is greater than the P du and P bubble, in less than P bubble point, okay, this means separation will occur. Okay. I mean, this is given by Raoult's law concept, right. Now, the next question is how to get the composition. So, once you have formulated this, the next thing is to do a material balance, all right. So, you can write down the equation of material balance, right. Now, you have all the information. So, let me just write down. So, this is here n dot is equal to V dot plus L dot, right, and then you can do individual one of the component balances. Overall of balance n dot is equal to L dot plus V dot, and let us say component 1 balance, we do W1 n dot is equal to x1 L dot plus y1 V dot. Okay. So, there are 4 unknowns. Okay, right. So, we can try to 4 unknowns, then we must have also 4 equations we have to write, right. So, let us write down. So, one is of course tell moles per second is equal to L dot plus V dot, then you have 0.5 10 moles per second equal to x1 L dot plus y1 dot V. Now, since it is a saturation, we are going to use the conditions of 7 kilopascal, okay, multiplied by y1 at the final exit. P into y1 is equal to x1 and saturation for individual component. Okay, this is for component 1, and 7 kilopascal 1 minus y1. So, basically I am just writing down the Raoult's law for component 1 and 10.56 kilopascal. So, you have 1, 2, 3, 4 equations, 4 unknowns. So, you should be able to solve this. Now, in order to solve this, one you have to make use of some kind of program. Okay. So, one of the simpler way to handle is to use Excel solver. Okay. Okay, or you can write a MATLAB code also, it will be very straightforward to do that. Okay. So, if you do this exercise and the final expression or answer comes out to be something like this. So, you can check this at your home. Okay, so this is the final expression. So, let us recap what we did. So, we have taken 10 mole per second of an equimolar liquid mixture of water and ethanol at 30 degrees Celsius and 11 kilopascal and flashed it to 7 kilopascal. A liquid stream exited the flash unit at 7.11 moles per second with a composition of 56% water, while a vapor stream also exited the flash distillation unit at 2.89 moles per second with a composition of 34% by mole water vapor. Thus, we have somewhat separated our equimolar liquid mixture into a liquid portion that has an enhanced water composition and a vapor portion that has enhanced ethanol composition. The more volatile component, which is ethanol in this case, is concentrated in the vapor phase. That is what you expect. Okay. So, everything is beautiful, right? In reality, what happens? In reality, the recap provided is not what happens, and why. So, that is important. So, everything looks mathematically correct, but beautifully we segregated it, but this is not what the reality happens. So, in reality, at this condition phase separation will not occur. So, let us look at why. So, this is the pressure and composition of mole fraction. Okay. It is not isotrope one. If you look at this dashed line, this is the phase diagram due to Raoult's law, but the blue line, the solid blue line is basically the real phase diagram from the experiment. Okay. Now, we are talking about 0.5. Okay. So, this was initially 11 and 0.5, right, and if you look at the system pressure is 7. So, what do you see? So, it will flash completely to vapor, it will not phase separate. If you had used Raoult's law, of course, it shows that this system pressure is between the dew point and bubble point pressure, but in reality it is system pressure is below the dew point pressure, and that is the reason that the work which we did will not be realized in reality. Okay, it will flash completely to vapor, from the liquid to vapor it will go. So, which essentially means that knowing that water and ethanol is not on a very simple system, okay, it hydrogen bonds also, we went ahead and used Raoult's law as a model, which was in fact not appropriate. So, knowing this, we should not have used that, and that is something which is important, and this is an example where we should conclude that just because a model provides an answer, it does not make it right answer. Okay. The chemical engineer is tasked with identifying what models to use and when to use them in order to make reasonable estimation for analyzing processes. Here we already knew that the water ethanol would not behave like an ideal solution. Okay. So, here we already knew that the water ethanol system would not behave as an ideal solution. Thus, using Raoult's law as a model for this system was from the start not a reasonable strategy, and this was validated in comparing the model results to that of experiment. So, this is something which we can conclude based on this exercise. So, the important thing is the models are important because it helps us to solve problems when no experimental data exists, but having a bit of understanding of the system would help you to find out the right model, because there are a lot of people who have already looked into the model, analyzed the model and quantified the model in terms of the appropriateness of the type of the systems which it works well. So, using that cue, one should be able to choose the right kind of model for a given system. Now, let us see how we can address this part using a modified Raoult's law, okay, where basically we are going to consider the liquid phase is non-ideal, and hence we will bring in the gamma. Okay, so now again we are going to put it in a different one, but here instead of water ethanol we are going to consider different system. So, let us look at the problem again. So, here is a 10 moles per second of an equimolar mixture of methyl ethyl ketone, and toluene is flashed from 760 millimeter Hg to 460 millimeter Hg at 75 degrees Celsius. You know experimentally that the infinite dilution activity coefficient of methyl ethyl ketone in toluene is 1.44 at this temperature. Likewise, you know that the experimental value for the infinite dilute activity coefficient of toluene in methyl ethyl ketone is 1.33, okay, at this temperature. So, these are the information is given. Solve for the composition and amount of each equilibrium phase as a result of the flash if the liquid is treated as an ideal solution, if the liquid is treated as a model by two parameter Margulis equation. Okay. So, this is the problem which we have. So, this is the point is I am not taking it, is basically is the given statement in the problem. So, let us try to solve, see what we can make use of it. Okay. Of course, you can maintain the temperature also, but usually temperature will vary. Okay. But let us look at this problem again and then see whether what you are making is going to change anything or not. So, what is saying that is 460 mmHg at 75 degrees Celsius, that is the condition at the flash state. Alright. So, now in order to solve this, you must ask the question, does the system flash at all, does it flash partially, does it flash fully, okay. And then since the first part is that if you want to use the Raoult's law model, let us start with that, that will be the first part. So, again we will be using Raoult's law, okay, and the first question is basically we are going to find it, the bubble point and dew point pressure. Okay, so let us look at the bubble point, okay, and you use again the Antoine equation. From the literature you find out this information. Again you can take a look at first at the NIST website for the details. So, this is the saturation pressure at 75 degrees Celsius. So, we are looking at the final condition. So, the initial inlet temperature may change, but we are looking at the final temperature, the system conditions. So, P2 sat is given and this is also given. So, once this is given, you can find out the pressure. So, this pressure is 0.5, 657.6 mmHg plus 0.5, 244.3 mmHg. Okay, it turns out to be 450.9. Now, this is the bubble pressure or bubble point pressure, and what is the pressure given here is 460 mmHg is. So, basically this is less than the 460. What does that mean? So, P bubble point pressure is less than P system. So, which means, so this is below the bubble point. Look at so you are talking about pressure. So, this is 450 is below the system pressure, thus it will not flash. That is given by the Raoult's law model. So, no suppression. Okay. Now, let us look at this is what is being said, the bubble point pressure is below the system pressure, the system will not flash and no suppression will occur. So, everything so thus the material balance is trivial as we still have an equimolar liquid mixture of this, okay, and the part A of the problem is solved. What about the if you had used modified Raoult's law? Again, if you had used modified Raoult's law, will the system behave the similar way as you have evaluated using ideal solution conditions? So, in order to do that, we write down again the gamma 1 x1 p1 sat. So, remember this, if you are using Raoult's modified Raoult's law, it is going to be py1 is equal to gamma 1 x1 p1 sat, right. So, this is a modified Raoult's law where the vapor phase is considered to be ideal, the liquid phase is non-ideal, and basically using the activity as a now the corrections to the non-ideality. So, P would be gamma 1 x1 P1 stat plus gamma 2 x2 P2 set. Okay. So, this is the basically the bubble point pressure which you have to calculate. Now, what is given to us is we have to use two state Margulis equation. If you look at the question, two parameter Margulis equation. Let me first write down what is the two parameter Margulis equation. It is basically nothing but G of E by RT is x1 x2 A 21 x1 plus A12 x2. So, you can say A and B also, does not matter, but this is the one which I am going to use now. Okay. So, this is the two parameter. Now, if you make use of the fact that from here you can get basically ln gamma 1 by taking by connecting the log gamma to the partial derivative of n times moles times G and T with respect to G and I. So, log of gamma 1 is going to be x2 A12 plus 2 A21 minus A12 x1. Similarly, log of gamma 2 is x1 square A21 plus 2 A12 minus A21 x2. All right. Okay, so the question is how do you find A12 and A21? If you look at the question here, the question what is given to us is also the infinite dilution. So, if you use this infinite dilution information, let us say plugging x1 to be 0, which means basically x2 is equal to 1. So, if you consider x1 to 0, which x2, yeah, x1 to be 0, which means infinite dilution, which means x2 is equal to 1, then ln gamma 1 infinity would be A12, right. So, in other word we are saying that ln gamma 1 infinity is limit x1 goes to 1 ln gamma 1, which is nothing but A12, ln gamma 2 infinity is limit x2 goes to 1 ln gamma 2 is A21, and this information is already given. So, this ln gamma 1 infinity is given in the problem statement. So, this is going to be log of 1.44, which is 0.3354, and this is going to be log of 1.33, which is 0.2846. Okay. First one, it should be x2 tending towards 1, and this will be x1 tending towards 1. Okay. Alright, so you have this information. So, now we can plug in this here in this expression of bubble pressure point, bubble point pressure. This is going to be gamma 1 x1 P1 S plus gamma 2 x2 P2 S. Okay. So, what is the, now this information is there. So, what is your gamma 1 at 0.5, x1 as 0.5 is 1.074, gamma 2 at x1 as 0.5 is 1.095. So, basically at equimolar mixture you have this information, you plug in here. So, this will become 1.074, 0.5, 657.6 mmHg plus 1.095, 0.5, 243.3 mmHg. So, this is going to be 486.9. So, which is basically the bubble point pressure. It tells you that it is above the system pressure. Okay. So, which essentially still does not address our problem. So, we will be also finding out the dew point pressure. So, we use again the dew point pressure to find out, and so if you consider again the modified Rawls law, So it is going to be Py1 by gamma 1 S, P1 S is equal to x1, right? Py2 by gamma 2 P2S is equal to x2. So here we are going to find out the y's, so essentially the dew point, right? So we are going to get P1 y1 plus gamma 1 P1 sat plus Py2 plus gamma 2 P2 sat is equal to 1. From here we can find out the pressure. So P is 1 by y1 by gamma 1 P1 sat plus y2 gamma 2 P2 sat, and if you plug in here 0.5, the gamma 1, this turns out to be 338.2 milli Hg. So it tells you that the system pressure, okay, is greater than P dew point and less than P bubble point. Okay, so basically it tells you in between it is lying. Okay, and thus now this would mean that this is phase segregated, which was not able to captured by the Raoult's law thing. So you again write down the energy balance. Okay, so you have 10 millimoles per second is equal to L plus V dash, 0.5 10 millimoles per second, this is going to be x1 L y plus y1 v1, and then again you are going to use that the Raoult's modified law, okay, where you are going to consider force, the pressure P 460 mg y1, and this is going to be 460 y2, and this is going to be x1 gamma 1 P1 star. Okay, so you know x1, you know your P1 sat. The gamma you can now write out in terms of exponential. See, gamma is this, right? So gamma 1 would be exponential of this term. So I am going to write here simply the exponential 1 minus x1 square a12 plus 2, okay, and similarly here 1 minus x1 244.3 msg exponential of basically the terms which you see it here, okay, here. So this way you have 4 equations and 4 unknowns. So if you solve it using Excel or MATLAB, you should be able to get the following answer. Okay. So this is what I wanted to discuss in this lecture, describing 2 different problems where the Raoult's law has failed, right, and that's why the importance of this understanding the system and utilizing the activity models becomes important. Now, if the vapor phase had been more non-ideal, then you have to use Fugacity coefficient also, which of course I am not covering here, which you can do that. The rest of the process is similar. You have to just make use of the Fugacity coefficient using some equation of states. Okay, so with that I will stop and I will see you in the next lecture.